This is lecture 5 of solid state physics, and we are going to start on quantum mechanical aspects of solid state physics today, particularly the electronic properties. So, let me recall that we did Ruder model last week with its successes and failures, or I would say shortcomings. So, two shortcomings that I said I will address in the coming week are: number one, that C experimental, the specific heat of metals is proportional to T, but Ruder model gives C equals 3 by 2 NkB, and this is not correct. The other one is Wiedemann-Franz law, which gave a ratio of 1.1 times 10 raised to whatever, whereas the correct ratio is some close to 2.2. So, these two things can be addressed by looking at electrons in quantum mechanical way. So, what we are going to do now, develop quantum mechanical way of looking at free electrons. So, keep in mind that I am still looking at free electrons. So, the electrons are moving in a constant potential. I am taking V equals 0. So, the ionic background is still ignored, and we will see that when I bring in quantum mechanics, these two failures or shortcomings can be addressed, and then we will slowly build up from there as to how more and more properties can be included as I improve my treatment. So, let me start with how quantum mechanical principles affect C, V, C, P. So, before I start, let me raise this question for you, and that is, in a solid, let us say it's metallic, how much is the difference between Cp and Cv? So, to start with, I will take electrons in a one-dimensional box. So, what I am doing is, I have this box and there are these levels in this. Each level has 2 electrons. maximum. So, let us just do a quick calculation. So, in this case the wave function psi x, let us call it nth level, is equal to square root of 2 over L sin n pi over L x, where I have taken the box to be between x equals 0 and x equals L. The energy of the nth level is equal to h cross square pi square over 2 ml square n square. Since I am taking a one dimensional box, let me take the linear charge density or linear electron density, linear number density of electrons to be 10 raised to 30 raised to 1/3, which is 10 raised to 10 per meter, or roughly 10 raised to 8 per centimeter. That is the linear charge density I am talking about. So, I want to fill in 1 centimeter 10 raised to 8 electrons. So, that is number 1. Point number 2, therefore, take the length of the box to be 1 centimeter. So, let me see the kind of picture I am developing. Is that I have this box of length 1 centimeter and there are 10 raised to 8 electrons in it. And since each level fills 2 electrons, so the number of levels to be filled is equal to 5 times 10 raised to 7 levels. I am filling that many levels. So, let us calculate highest energy. Level occupied is going to be h cross square pi square over 2 ml square n square, and you put in numbers, they come out to be h cross square is 10 raised to minus 68, pi square is 10 over 2 times m is roughly 10 raised to minus 30 kilograms. L is 1 centimeter, 10 raised to minus 2 meters. So, 10 raised to minus 4 meter square times n square, 25 times 10 raised to 14. You do this calculation, this comes out to be roughly 8 electron volts. So, it is filled up to, let me go back to this picture, about 8 to 10 eV. Difference of energy between two levels is going to be of the order of 8 over 10 raised to 7 levels. So, roughly 10 raised to minus 6 eV. So, you can see that these levels are actually filled pretty much continuously. Okay, so, let me make it with a thick ink. So, up to this level you can't really distinguish between two levels. This is how this box is filled. Let me make the outer line also thick. If you want to calculate exact difference, it will be h cross square pi square over 2 ml square n plus 1 square minus n square, and for n equals 5 times 10 raised to 7, this comes out to be about 3 times 10 raised to minus 7 eV. So, that is the kind of difference between two levels. So, I call them quasi continuous. because they are roughly continuous. Now, coming back to this picture again, this is the box and this is how it is filled. Up to about 8 eV. Now, let us calculate how much energy can an electron take at roughly room temperature. So, this is 1.4 times 10 raised to minus 23 times 300 Kelvin, which is roughly 25 MeV. So, the number of levels in this range kBt is equal to 25 times 10 raised to minus 3 divided by 10 raised to minus 6. That was roughly the difference between two levels. So, that is 25,000. Now, imagine here are about 10 raised to 7 levels and kT makes a difference only in 25,000 levels, right. So, if I go to again very grainy picture, these are the levels. Here are these electrons. Imagine this to be roughly 10 raised to 7 levels. So, this electron by thermal energy cannot really go anywhere, because 25,000 will be like a thin line out here. So, this electron cannot get excited by thermal energy. This electron cannot get excited, this electron cannot get excited, only a very thin line out here representing about 25,000 levels. These are the electrons that can gain energy and go up. All these electrons down here are inactive thermally, nothing happens to them. So, you can say, if I make this picture roughly out here, only this thin layer participates in the thermal process. So, I can say that the number of electrons participating in thermal process is roughly proportional to kBt. The rest do not participate, and each electron carries delta E roughly kBt. So, change in the energy of the system is roughly kBt square, and delta E delta T therefore will be proportional to T, and that is Cv. So, this gives you roughly an idea that when I bring in quantum mechanics, the specific heat is proportional to T. Let me ask you a question here, why is this Cv and not Cp? So, let me summarize what we have learnt. We have learnt, number one, because of Pauli exclusion, principle, only a small fraction of electrons participates in thermal excitation. Rest cannot take energy and go to those levels which are already occupied. And number 2, because this number delta n is proportional to T, delta E is proportional to T times k B T, proportional to T square, this gives C V proportional to T. So, what we have learnt is that because now these levels are filled because of Pauli principle, no longer equipartition is valid, and that causes only a small fraction of electrons to get excited, and therefore, very small energy is taken, and that energy change comes out to be proportional to T square when you raise the temperature by T, and that gives you the answer for CV proportional to T. So, this is a result of equipartition theorem not being valid in quantum mechanical systems. That is, each electron does not have energy kBT, they are distributed, they are going from 0 to roughly 8 electron volts. All right. So, this is the kind of argument, a physical picture that I have drawn. Now, let us go into nitty gritty. Question 1. When developing quantum mechanical picture, should we take particles in a box, which I just now did to develop the argument, or wave function for free particle? And I am raising this question because some books, Kittel actually uses the particle in a box picture. But let us try to answer this now. So, particle in a box has these wave functions like this, second one is like this, and so on. Now, if you look at the Hamiltonian for free particle, which I said that particles are moving in constant potential, is going to be minus h cross square over 2 m d2 by dx square in 1D. The Hamiltonian commutes with px, and this implies that px is a good quantum number. So, wave function should be an eigenfunction of px also. That means, they are well defined momentum states. Now, if you look at sine n pi over Lx, which is a combination of e raised to n pi over Lx plus e raised to minus n pi over Lx over 2I, is not a momentum eigenstate. So, the correct free electron picture is going to be that my wave function which is a solution of h cross square over 2 m d2 psi by dx square equals E psi would be e raised to I k x, where h cross square k square over 2 m is equal to E. And I do not take the linear combination of this with minus k x, that will give me sine, but that is not an eigenfunction of p. Notice that p x e raised to I k x is equal to h cross k e raised to I k x. So, it is an eigenfunction of p x also. The second reason, therefore, or you can say related reason for taking this wave function is that what you are going to learn through the question I am going to give you now. Plot density of, let us say, 1000 particles in a box. Is this density uniform? The answer to the second part, whether this density is uniform or not, is no, it is not uniform, because when I take this box, the wave function is 0 out here. So, density is going to be something like this, it will go here and then it decays down. So, I am answering that for you, but you should plot it and see it for yourself. Density is not uniform. On the other hand, for a bulk system, density is indeed uniform. So, these sin k x wave functions do not really work well. If you take e raised to I k x times psi star e raised to minus I k x, it comes out to be 1. So, in this case density does come out to be uniform. So, what we conclude is that the free electron, free means there is no boundary, wave function is psi k x, k represents the momentum, equals some normalization constant e raised to I k x. That is the wave function. Psi star psi is uniform. So, that is settled. Once I do that, the next question that arises, how do we normalize this wave function? Because uniform, if I integrate from minus infinity to infinity, this comes out to psi star psi dx is going to come out to be infinity. So, now we do a mathematical trick. I am calling it trick, but actually mathematical device you can say for normalization and counting of states, and this is known as periodic boundary conditions. These keep the wave function as e raised to I k x. That means, they keep the wave function to be eigenfunction of the momentum operator and facilitate normalization and also counting of states. So, let me introduce that. So, we are dealing with periodic boundary condition for psi k equals c e raised to I k x. And again, it is a mathematical device, mathematical method of dealing with such states where k otherwise would be continuous. So, what I demand is that psi k x plus L be equal to psi k x. That is, the wave function is periodic with period of length L. L is tending to infinity, it could be taken quite large. So, what we have is psi k x plus L equals e raised to I k x plus L, which I want to be equal to psi k x, which is e raised to I k x, and this gives you that k L should be equal to 2 n pi, n equals 0, plus minus 1, plus minus 2, and so on. And therefore, the k values are 2 n pi over L, n equals 0, plus minus 1, plus minus 2, and so on. Since L is tending to infinity, delta k, which is 2 pi over L, is tending to 0. So, the levels are quasi continuous. That means that although they are grainy, the difference between them is 2 pi by L, but that difference is very small, right. So, these levels are like this, and the difference is much smaller than the extent over which they spread. So, that is why they are kind of quasi continuous, and that means if they are quasi continuous, all the summations, and this also has implications, all summations can be done as integrations. So, one thing we have now settled, that these wave functions are going to be of the form psi k x equals c e raised to I 2 n pi over L x. Now, the next question is normalization. Normalization of psi k x. This is done over L, and that means what I want is psi star k x psi x dx from 0 to L p equal to 1, and that gives you c square, I am taking c to be real, times L equals 1 or c equals square root of 1 over L, and therefore, these free electron wave functions psi k x are equal to square root of 1 over L e raised to I k x, k is 0, plus minus 1, plus minus 2, and so on. These are the wave functions. K equals this, no, n equals 0, plus minus 1, plus minus 2, and k equals 2 n pi over L. So, if I were to draw a k line, let us say this is k equals 0, k increasing this way, every 2 pi by L there is a state, it keeps on going on the other side also, and there is one at the origin also. So, this is one state. Although I have shown this distance to be large, is actually going to almost 0. So, I can write that every 2 pi by L equals delta k, there is one state. So, density of states is equal to 1 over 2 pi by L per k, which is equal to L over 2 pi. It makes sense to talk about density of states, because as I said, these are quasi continuous levels. So, I do not really have to count, I can just write the density times dk is the number of states in delta k, right. So, this means that number of states in delta k is going to be L over 2 pi times delta k. So, what I have set up is that on this k line 0, 2 pi by L, 4 pi by L and so on, there are these states, minus 2 pi by L, minus 4 pi by L and so on, there are these states, and every 2 pi by L carries one state. I have shown them far apart, they are very close by, and if I take a delta k range, then the number of states in this is L over 2 pi delta k. That is the setup for our one dimensional free electron gas. Now, let us do some calculations. So, suppose there is a 1D electron gas with lambda electrons per unit length. I should be then able to calculate all the numbers, energies through whatever I have developed so far. So, if I go in K space, I am going to have all these states filled, since plus and minus k have the same energy, the states are going to be filled symmetrically. So, we have states from minus k f, I will tell you what k f is, to plus k f filled. Filling is symmetric because energy of k equals energy of minus k equals h cross square k square over 2n. So, number of states in 2 k f is going to be equal to 2 k f times L over 2 pi. So, this k f is called Fermi wave vector, and since each state carries 2 electrons, so the number of electrons is going to be 2 k f times L over 2 pi times 2, which is equal to 2 k f L over pi, and that gives you equal to n, which is number of electrons. So, what we have found, if there is a one dimensional system in which there are n electrons, then I have 2 k f times L over 2 pi times 2 equals n. This 2 cancels, 2 k f L over pi equals n, or k f equals pi n over 2 L, which is pi over 2 lambda. Lambda equals n over L equals number of electrons per unit length. So, if I have a system where I have lambda per unit length electrons, in the k space I have levels from minus k f up to k f filled. All these states are going to be filled. So, I have defined for you something called the Fermi wave vector, which is the highest occupied k state wave vector. The corresponding energy is known as Fermi energy, which is energy for kf. So, epsilon f is going to be h cross square kf square over 2 m, which is h cross square over 2 m. Kf is pi lambda over 2 whole square, which is h cross square pi square over 8 m lambda square. So, we have found Fermi wave vector kf, Fermi energy epsilon f, and let us now find average energy per electron. Now, this I have to be careful about, because I am filling all these states. So, if I take a particular delta k, the energy of electrons, if this has wave vector k, is going to be h cross square k square over 2 m, and the number of states here is delta k times L over 2 pi, and number of electrons is times 2. I integrate this from minus kf to kf and divide by n, that is E average. And you carry out this calculation, and you are going to get equal to 1/3 epsilon f. So, in 1D, average energy E average is equal to total E over n, which is epsilon f over 3. I would give you a question here, show that or calculate kf and epsilon f for a 2D gas. The final concept I want to talk about now is the density of states. As I said earlier, these states are quasi-continuous. So, I talk about density of states, and when we talk about density of states in this language, this means number of states in energy range d E is given by d E times this delta E, which is equal to number of states in energy range d E, and this d E is known as density of states. This is very easy to calculate, because I have already calculated how the number of states are counted in K. So, let us quickly do that calculation. d E is going to be equal to d E over d k times d k, and this gives me density of states in K space, right. So, d E d k is number of states in the range d k, and this is equal to L over 2 pi. I also know that E is h cross square k square over 2 m. That means d E d k is equal to h cross square k over m, which is equal to h cross square over m 1 over h cross square root of 2 m e. You put all this in and you get d n d e, which is d e, which is number of states per unit range of E, and also let us put it per unit length, because I want to make it an intensive quantity, and this comes out to be d n d e, which is equal to 1 over 2 pi h cross square root of m over 2 e. If you include spin, that means there are 2 electrons per state, then d n d e, which I will write as d e, is equal to 1 over pi h cross square root of m over 2 e. So, density of states goes as 1 over square root of e in 1D. So, let me summarize this lecture before I go on to 3 dimensions, which I will do in the next lecture. I will summarize so, number 1, we have shown that filling of orbitals due to Pauli exclusion principle prevents all electrons to participate in thermal excitation. Although I have talked about thermal excitation, this will be true for any kind of excitation. Until you provide proper energy, no electron from the bottom of the filled electron C level k levels is going to be excited above the Fermi energy. So, it allows only a fraction proportional to k b T over epsilon f of total number of electrons to gain energy, which is roughly k b T, and this leads to T dependence of C v. Then we have developed free electron model in 1D, and therefore introduced concepts like Fermi wave vector, Fermi energy, and density of states for free electron model. And we will take these concepts over as we develop solid state physics further, but we are going step by step. So, next lecture I am going to do all this for 3-dimensional electron gas. Thank you.